when I look at the momentum of my body, it's going to be the mass of my body, which is a lot bigger than my leg, times the velocity of my body. So to get the velocity of my body going up over here, which determines how high I can hop, I move the big N to the other side, and I get small n divided by big N times the velocity of my leg. Now, the leg of my body, the mass of my leg only takes like a little bit part of the entire mass of my body. So let's say the ratio between the mass of my leg and the mass of my body is like 1/10. Okay? So you see, because momentum is proportional to the mass, I need to share all the momentum in my leg with my entire body. So the momentum that each part of my body gets is small, so the body will move up with a small velocity. The velocity of my body after I hit my leg will be suppressed by this factor of mass of leg over mass of body. I say it's about 1/10. I'm not a biologist. I don't know how human body works, but it's a guess. And if the velocity is suppressed by 1/10, the height over here, which is proportional to velocity squared, will be suppressed by 1/100. So you see this initial speed is important, and because it is suppressed by the mass ratio between my leg and my body due to momentum conservation, the height I can end up jumping is not that big. Okay? Any question? So that is momentum conservation. So there's a effect in fluid called conduct effect, which is kind of related to momentum conservation. And I want to mention it because it is the correct explanation of most fluid example you see in other textbooks. But they don't use it. They don't use conduct effect. They use Bernoulli's principle, which is wrong. Actually, let me try it if this will work. So this is the hair dryer. It blows air. I can try to support the ping pong ball with the air. Not impressive at all. That's just for the video. This hair dryer is not strong enough. This is a video from Harvard, I guess.
What do these two things have in common? The Coanda effect. We can use our Schlieren optics setup to actually see how the air flows past an object. Here's a cylinder, cardboard cylinder, and my source of air is going to be simply a hair dryer. And as I bring the hair dryer closer and closer, you see the flow of air is straight, but when it is close to the object itself, the air gets deflected downward. It follows the contour of the cylindrical object. When it's far away, it goes straight. This is true for any object. Here's a spherical object, a basketball. Again, if I bring the airflow close to the basketball, notice how it gets deflected downward. It tends to wrap around and follow the contour of the ball. So you notice when the air is far away from the ball, it just goes straight, whereas as I get closer and closer to the ball, it actually follows the contours of the ball and curves around. What's going on? Why does it do that? Well, we can understand it by assuming there's friction between molecules in the air. We call that viscosity. So if you assume for a moment that the air is going to go straight and not deflect, molecules that are sitting underneath the airflow feel a friction force to get dragged along with the airflow and leave that area, producing a reduced pressure area here. And it's reduced compared to what's up above. And so there's a net force that pushes the airflow down and it continues to curve around the ball. And that's the Coanda effect. Let's have a look at a ping pong ball being supported by a jet of air, again supplied by our hair dryer. Notice as I tilt the hair dryer, the ball remains in the stream of air and is still levitated, but also notice how the bottom of the ball is deflecting the air so it wraps around. The air follows the contour of the shape of the ball. It's really annoying when you're pouring wine and the wine drips down the side of the bottle. We can thwart the Coanda effect by making the lip of the bottle really sharp. We can do that with a piece of foil, which I'll roll up and put into the bottle. And no drips whatsoever.
Okay, so let's count our effect. What you see is that the air can support the ping pong ball without letting it dropping. So the hair dryer blows out the air with initial momentum going this way. The ball is trying to fall, but the air on top of it will be curved downward, and the final momentum is going this way. Momentum is conserved. So it means that the ball must get an upward momentum to go back into the air. So that's how the hairdryer can support the ping pong ball with contact effect. Contact effect is the fact that the air will be curved around the surface. The part of momentum conservation is that if you curve or if you change the momentum of the air, the momentum does not go disappear. The momentum of the air is not destroyed, but goes into the momentum of the ball. Okay? Now, after the ball flies up, when the ball is too high, the air will curve in the other direction, causing an upward momentum change. So when the ball is too high, the air will change its momentum by getting an upward momentum. Now, momentum is conserved, so vertical component should be 0 in the initial and final state. So at the final state, if the air gets an upward momentum, what will happen to the momentum of the ball?
Go down.
Good. So when the ball is too high, it will go down because momentum is conserved. If the ball is too high, air will curve up, getting an upward momentum. To conserve momentum, the ball must get a downward momentum, so it will go back down. And then when it goes back down, the air curves down, getting a downward momentum. To conserve momentum again, the ball will go up, and then it will go up. When you look at a video, the ball is not staying at a fixed location. It is oscillating up and down. But because when it's too low, the air will give it an upward momentum. And when it's too high, air gives it a downward momentum. So at the end, it will stay oscillating around that area and be alleviated by